The Mystery of High-Energy Cosmic Rays. Presented by Science at NASA. Hold out your hand for 10 seconds. A dozen electrons and muons just zipped unfelt through your palm. The ghostly particles are what scientists call secondary cosmic rays, subatomic debris from collisions between molecules high in Earth's atmosphere and high-energy cosmic rays from outer space. This daily shower, which never stops, is a sign of violent events in deep space. It's believed the majority of cosmic rays come from supernova explosions. When massive stars explode, they blast most of their material into space. The expanding shock waves can break apart interstellar atoms and accelerate the debris to unimaginably high energies. Other unknown cataclysmic phenomena may be at work too, especially for the most energetic cosmic rays. Eun-Suk Seo, a professor of physics at the University of Maryland, says, cosmic ray particles with energies as high as 10 to the 20th power electron volts have been measured on the ground. This is more energy than we have achieved in the most powerful man-made particle accelerators. But how do natural cosmic ray accelerators pump so much energy into these particles? This is one of the biggest mysteries in astrophysics. While indications of the energies of cosmic ray particles can be measured from the ground, Seo and colleagues have taken their study to higher elevations, directly measuring particles from space before they break up in Earth's atmosphere. The cosmic ray detector known as CREAM, the Cosmic Ray Energetics and Mass Investigation, has been launched to the stratosphere above Antarctica on board long-duration helium-filled balloons. By lofting the detector above 99% of the Earth's atmosphere, researchers get a better idea of what cosmic rays are like before they collide with nuclei in the air above the detector. CREAM is able to measure the energy and direction of each incoming cosmic ray particle and identify the particle type by measuring its charge, thereby providing clues to the particle's origin and acceleration mechanisms. Since 2004, the team has flown CREAM 7 times over Antarctica, accumulating more than 191 days of data from altitudes as high as 120,000 feet. They're about to go even higher. CREAM is heading for space. A reconfigured CREAM detector is scheduled to travel to the International Space Station in 2017 aboard SpaceX's Dragon spacecraft on a Falcon 9 rocket. Named ISS CREAM, it will remain installed on the Japanese experiment module, also known as Kibo, for at least 3 years. Seo says the ISS provides an excellent monitoring platform for high-energy cosmic rays. The station allows for long-term monitoring in lieu of multiple limited-duration balloon flights, providing direct, unimpeded access to incoming cosmic rays without atmospheric interference. The longer exposure times on the space station allow for the measurement of higher energies. ISS CREAM has a goal of measuring the highest energy possible for direct measurement of high-energy cosmic rays. She adds, the mysterious nature of cosmic rays serves as a reminder of just how little we know about our universe. For more high-energy science from beyond Earth's atmosphere, stay tuned to science.nasa.gov.
At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.
So tonight we're going to hear the talk about the electricity of extensive layer clouds. So the abstract that Keri's provided is that stratiform clouds constitute approximately 40% of global cloud cover and play a key role in determining the planetary radiation budget. Electrification remains one of the least understood effects in the microphysical processes. Charging of droplets at the top and bottom edges of stratiform clouds arises from vertical current flow through clouds driven by the global atmospheric electric circuit. In this talk, Dr. Nicoll will discuss the current state of knowledge surrounding the effect of charged cloud and droplet properties. This will include how charge is generated in stratiform clouds, typical magnitudes of charge and droplets, techniques to monitor cloud charging, and evidence for electrical effects on large-scale cloud properties. So the usual process is we'll hear a talk from Keri, and then we'll have a question and answer afterwards, both from the floor and both from virtual. So over to yourself, Keri. Thank you.
Thank you. I think I should have written a shorter abstract. Okay, so thank you for having me here tonight. It's nice to be back in Edinburgh. So this is where I did my undergrad physics degree many years ago. So tonight I'm going to talk to you about stratiform clouds. So most people, when you say stratiform clouds, they get rather depressed. They think they're the dullest, most boring type of clouds on the planet. And that's probably true, but I get excited by them. Hopefully by the end of this talk, you'll understand why that is. So the reason that we're interested in these clouds is that they're actually electrified. And this is not something that a lot of people know, but by the end of this talk, you will also be experts on this. So the reason that we are interested in these clouds is they become charged, and that charge can influence the cloud microphysical processes inside the clouds, and that may have potential implications for climate. So I'm going to talk you through all that tonight. So we will start off discussing how these clouds become charged, how we know they're charged, and that's through some measurements that we've made with bespoke balloon instrumentation that we've developed at Reading. I'll then discuss what the effect the charge has on the droplet behavior. And then I'll talk about some novel experiments that we've been doing in fogs to demonstrate or to try and find some evidence whether charge affects cloud properties in the real environment. And then finally, I'll discuss what the implications of this are for weather and climate. Because this is very much an understudied effect. It's not included in climate models, and it's not widely studied. So there's lots to learn about it. So we'll start off discussing where the charge comes from, basically. So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. So this charge is being generated all the time. And initially, the charge exists in the form of really tiny nanometer-sized charged ions. But they don't stay tiny for long because they interact with atmospheric molecules and aerosol particles and droplets. And this is the subject of a totally different talk, or three totally different talks, but I just wanted to make you aware that charge can actually affect many different types of aerosol and droplet processes. Some of the things that we've studied, for instance, is the charge effect on long-range dust and volcanic ash transport. So the idea here is that the charge can maintain the dust or the ash in the atmosphere for longer than it would be normally. And this might explain some strange observations of large dust particles that are transported huge distances, and nobody can explain why. Another thing that charge might affect is the radiative properties of dust layers. So there's been some theory and measurements that suggest that the particles can align in the electric field and act like a Venetian blind type effect, which affects the amount of solar radiation that's transferred through a dust layer. And then the other thing, which is what we're going to talk about tonight, is the effect of charge on cloud microphysics. So another concept that's important here and that's related to charge in the atmosphere is something called the Earth's global atmospheric electric circuit. So I should probably move this because you can't actually read the title of these slides. So the global circuit, not much better, is it? It's okay, it's fine, good point, it disappeared, sorry. So the global circuit is a hypothetical concept which describes current flow around the planet, basically. Why are we not moving? There we are. Okay, so this was suggested by the Scottish physicist C.T.R. Wilson in the 1920s. So this is the same C.T.R. Wilson who invented the cloud chamber, but he also worked in atmospheric electricity. And in this circuit, we have Earth's surface and the ionosphere, which is a layer in the atmosphere about 60 kilometers up. And these are highly conducting regions. And the idea is that we treat these two surfaces as the plates of a spherical capacitor. And in the middle, we have the atmosphere, which is weakly conducting because of the ionization from the cosmic rays and the radon. And this charge that we have, this positive and negative charge, becomes separated in thunderstorms. So the top of thunderstorms become positively charged and the bottom become negatively charged. And this charge is transferred up into the ionosphere and the negative charge is transferred down to their surface. This creates a huge voltage difference or potential difference between these two plates of the capacitor, which we call the ionospheric potential. And it's about 200,000 volts. So if you were to connect a wire between the ionosphere and the Earth's surface, there'd be a 200,000 volt difference, which is enormous. And that voltage difference, and because we've got charge carriers, means that we have a tiny little current which flows, which we call the air-earth conduction current, or JC. And it flows everywhere. So it's not just related to thunderstorms. It flows in all fair weather regions of the atmosphere. It's flowing right now. So the two things that you've got to remember as we go through this talk, the two concepts are this vertical conduction current, JC, and also the concept of an electric field. So this global circuit sets up an electric field in Earth's atmosphere, which again is everywhere. And near the surface, it's about 100 volts per meter. So that means there's about 100 volts between my feet and about here. We also call it the potential gradient. So I'll use electric field and potential gradient sort of interchangeably in this talk, but they basically mean the same things. It's just one's the negative of the other. So we've got a conduction current density and we've got an electric field set up by this global circuit. So what evidence is there for this global circuit in the atmosphere? So the idea is it's driven by thunderstorms. So as I say, this idea was first suggested in the 1920s. So in the 1930s and 40s, there was a lot of interest in investigating whether this concept was right or not. But in these days, we didn't have global lightning detection networks. We didn't know where the lightning was over the Earth. What we had was thunder day data. So this is an observer listening, saying, I can hear thunder today, and that's recorded as a thunder day data. So that means there was lightning and thunder on that day. And so through lots of painstaking observations and collating the data from all the observatories around the world, they managed to create this map of global thunderstorm activity. And so you see that there are 3 main thunderstorm chimneys on the Earth, one in the Americas, one in Africa, and one in Asia. And if you plot the surface of the Earth that's covered by thunder, or therefore lightning, as a function of time across the day, each of these blue curves is these 3 thunderstorm chimneys. And the time of day that it happens depends on the local afternoon time. So obviously local afternoon is first in Asia because that's when the thunderstorms happen. But when we plot it as GMT, it looks like this. And if you take the sum of all of these areas, then you get this global curve. But we're not used to looking at time backwards, if you like. So let's invert, or let's change it into what seems a bit more sensible to us. So 0 to 24. So the thunderstorm area changes like this throughout the day. There's a minimum in about 3 UT, and there's a maximum about 1900 UT. Now, at the same time, there was a wooden research vessel sailing the oceans called the Carnegie Research Ship. And this was making magnetic measurements and atmospheric electricity measurements. And it was measuring this electric field or potential gradient. And they found that regardless of where they sailed in the world, on a fair weather day when there was nothing else happening, they measured this diurnal variation in the potential gradient. And it's got a minimum at the same time. Well, you can see for yourself. The two look very, very similar. So not only, so the fact that they measured the same variation globally meant that there was something globally going on. And the fact that this matched with the thunderstorm activity really suggested that, okay, it's thunderstorms that are driving the global circuit. So what does this mean for our clouds? So as I said, this conduction current, which results from the global circuit, it flows everywhere. And when it encounters clouds, it creates, or specifically layer clouds, it creates charge on the edges of these clouds. And I'll describe that in detail in the next slide. But the point here is that this is a very understudied phenomenon. Most of atmospheric electricity has studied either thunderstorms or what we call the fair weather region, where there are no clouds. The semi-fair weather region, where the clouds are, has been largely neglected. So we don't know a lot about this. But these clouds cover 30 to 40% of the planet at all times, and there's an awful lot of them over the ocean. So this charging of these clouds is happening all the time, and we don't understand a lot about it. So that's a reason for looking at this. So how do these clouds become charged? Well, to do that, we have to think about some of these atmospheric electricity parameters a bit more. So we have to consider what's called conductivity. So conductivity is the ability of the air for a current to flow in the air. And it depends on this ionization from our cosmic rays and from our radioactivity. So these tiny little ions that are created in a cloud, they become attached to the droplets. And that means that the conductivity goes down when you have a cloud layer. So this is our cloud layer. We're going up through a cloud layer. So our conductivity decreases, is low in the cloud, and it increases when we get above the cloud. If we go to Ohm's law, which if you remember back to your school days, you probably did this in the form of V equals IR. It's basically the same equation, just written in a different way. And that says if you have a current, so in this case, JC, it's flowing through the cloud, and you have a conductivity or resistance, basically the same, the inverse, then if you have an electric field, then the conductivity and the electric field are inversely related if the current stays the same. So because we have a conductivity decrease, we must have an electric field increase in the cloud. And if we take another relatively simple law of electrostatics, so Poisson's equation, that says if you have a gradient in electric field, then you will create a charge, a space charge, rho. So you see that there's a gradient in the electric field on the bottom edge of the cloud and on the top edge of the cloud. So that means that we should get a charge, rho. And that's what we see here. So this is our charge density. So because of the direction of the field and the current flow, we should get negative charge at the base of the cloud and positive charge at the top. And if we manipulate these equations a little bit more, this charge depends on a few things. It depends on the conduction current, so our JC, which depends on the global circuit and therefore the thunderstorms. It depends on the conductivity, which depends on the ionization from the cosmic rays. And it depends on the gradient of the conductivity, which is this bit here, which depends on the height of the cloud, but also the cloud droplet properties. So if we have a really sharp cloud edge, we should see more charge than if we have a woolly one, if you like. So that's what theory predicts. So our theory predicts that cloud edges are charged and that the charge should be transferred to the cloud droplets. So what does this charging of droplets do? Well, we'll discuss this in a bit more detail shortly, but basically it affects the microphysical interactions between aerosol particles and droplets. And collisions and coalescence, which is something that's particularly important in clouds, is affected by charge. So this means that things like the lifetime of the droplets, how long they last, and how they grow can be affected by charge. And many of you will know that it's these small-scale cloud microphysical processes that determine the large-scale properties of the cloud, such as the height of the cloud, its opacity, or how much its reflectivity, basically, how long the cloud lasts, and even the rainfall. So do we have any evidence that the global circuit can affect clouds? And the answer is yes. So this is a really nice study by Harrison and Ambam, which looked at the height of the cloud base from two sites, one in Halley in Antarctica and the other in Sodankylä, which is in the Arctic in northern Finland. And they took the height of the cloud base measured by a ceilometer, and they looked at the polar night, because trying to find evidence of charge affecting clouds is very difficult, because clouds are inherently variable and there are lots of different processes going on. And charge is probably one of them, but in most situations, it's probably not the most important one. So if you can find conditions when all those other effects are minimized, you might be able to find evidence that this effect exists. So that's what's been done here. If you go to the polar night, so that's in the winter when the sun doesn't come up, you don't have any drivers, you don't have any solar drivers, you don't have convection, you wouldn't expect to see a diurnal cycle in the clouds because there's no sun. But what you find is that you do indeed see a diurnal cycle, and it matches very closely the diurnal cycle in the Carnegie curve, which I showed you a few slides ago. So yes, it could be coincidence, but I think this is quite compelling, that it suggests that the global circuit is driving the height of the cloud base in the Arctic and in the Antarctic during the polar night. And this research has since been confirmed in other places. So there's been a recent paper by Levine and Liu this year who found the same effect in Alaska during the polar night. And they went one step further, and they had measurements of long wave downwelling irradiance. So this is downward long wave radiation from the clouds. And they find that it's very well correlated with the cloud base height. So when the cloud base height changes, that changes the downwelling long wave radiation. And if you know your thermodynamics, then you would expect a change in the long wave radiation to affect the surface temperature. And that's what they find. So they find that in the polar night, the long wave radiation and the surface temperature are very well correlated, but not so much in the polar, sorry, in other times when it's not polar night. So we've got a correlation here between the electric field, which they also measured at the same site, the long wave radiation, and the surface temperature. And it all seems to be related to the global circuit. So I think this needs a bit further investigation. And we need to see whether this exists at other sites as well. So that's why we need to look at this effect a bit more. But a lot of what I've shown you is sort of theoretical and hypothetical. So what do we actually know about charge in layer clouds? Are they charged, for instance? So when I set out to start investigating this as a PhD student a long time ago, there were only a handful of measurements in clouds of charge. It's not an easy thing to do because you have to physically get into the cloud. So we decided to try and do this, and weather balloons were our chosen tool, because aircraft are expensive and you don't get very many shots at cloud layers. You know, you might get a couple of days where you can fly in clouds, because otherwise it's so prohibitively expensive. Whereas radiosondes are relatively cheap. They're flown all around the world as, you know, standard weather forecasting tools. So the idea is if you could instrument the radiosonde network, then you could get an awful lot more measurements. But you can't just go and buy a charge sensor. They don't exist. Nor can you buy, or certainly at that time, you could not go and buy a small cloud droplet sensor, an expensive one. So we had to develop our own. So in becoming an atmospheric electrician, I've also become an instrumentation scientist as well. So this is our charge sensor. So these bells here are the electrodes that sense the charge. And they are cat bells. You have to take the dinger out of them. You can buy them in John Lewis. It used to be 10 for £1, but it's probably more 10 like 10 for £5 now. And they are sensitive to changes in electric field. We have two. We have a linear one, a sensitive one, and a logarithmic one to measure larger changes in charge. And we developed an optical cloud droplet sensor. So this has light emitting diodes that shine light out. The light reflects back off the droplets into a photodiode in the middle. We use different wavelengths to tell us about the size. And so we fly these together on standard operational radiosondes. So this is what you see if you fly through a cloud layer. So this is the temperature. If you're just flying a normal radiosonde, this is all you would get. So you get the temperature profile. You see the inversion at the top of the cloud. Here's the humidity profile. This is what we get from the optical sensor. So the black line is the reflected signal from the optical sensor. I plotted it in terms of visibility here. So as you go into the cloud layer, the visibility decreases as you'd expect. And this gray trace is the photodiode voltage. So this is solar radiation. So as you go up through a cloud, it gets brighter, as you'd expect. This plot here is the theoretical conductivity decrease and the theoretical electric field or potential gradient increase, so like those profiles that I showed you a few slides back. And this is the charge that was measured in black. So you see here that we've got a layer of negative charge at the cloud base and a layer of positive charge at the cloud top. And the gray line is the modeled charge that we get from this here. And you see that that fits very well with the theory that I described a few slides ago, that we've got negative charge in the base and positive charge at the top. So that's just one cloud. We've since done many more. I said 30 flights here. We've probably got more than that now. I've basically done this all over the world. I've done it in Antarctica. I've done it in the Arctic, Iceland. I think that's supposed to be Portugal. And if you take the average, I should say that the charge in clouds is highly variable. All of these clouds are charged, just in different degrees of magnitude. But if you take them all together, then what you see is something like this. So the bases are generally negatively charged and the tops are positively charged. And we get about 40 picocoulombs per cubic meter. So that probably means nothing to you. What does that mean in terms of the droplet charges, right? That's what we're interested in here. How charged are these droplets? So if we take the measurements from the optical sensor and the charge sensor and put them together, and we assume that the charge is equally distributed between all sizes of droplets, then we can plot these distributions of droplet charges for the cloud base and for the cloud top. And you see that the median of these distributions is not large. It's on the order of a few electrons, which doesn't sound like much, but believe it or not, it is actually enough to influence some microphysical processes. But the interesting thing is the tails of these distributions. You can see here that there are some droplets that have hundreds of charges. And I should point out that the charge sensor is saturated in a lot of these clouds. So I think these charges are actually quite a bit more than what they are here. So that brings us on to, well, what does that level of charge, what effect does that have on the droplet behavior? So here I'm going to talk about some, I guess, theoretical considerations as to how charge can affect cloud microphysics. So the first one is the diffusive growth of droplets. So droplets can grow via condensation and they can shrink via evaporation. And you find that the surface tension of, basically charge can affect the surface tension of the droplets, which means that they will be more likely to form at lower critical supersaturations than if they're not charged. So if you look at Kohler curves and things like this, then you can work this out theoretically. And so what you find is that if the droplets, so the charge on the droplets is increasing in this direction, if you charge the droplets, then they form at lower critical supersaturations than if they're uncharged. And when they do form, they're larger droplets than what they would be if they're not charged. So this suggests that condensation and evaporation can be affected by this process, by charge. The other process that might be affected is collisional growth. So this is the other way that, well, probably the way that you think about cloud droplets growing in a cloud. It's by colliding with each other and sticking together. And that's described in terms of the collision efficiency. So the idea here is you've got one droplet and then you've got another one, and as it comes close to it, it can be influenced by the electrostatic force. And so if it's charged, then it's more likely to stick to that other droplet, and therefore they grow. And the reason this can happen is because of something called the electrical image force. So if you've got oppositely charged droplets, it's probably fairly obvious that they can attract each other. But everybody probably remembers from school that if you've got the same charged droplets, if you've got two positively charged droplets, we were all taught that Coulomb's law of repulsion means that they will repel each other. And that's true. But if you've got droplets, then it's different because the charge and the droplets can move. So Coulomb's law is for point charges, where the charges don't move. But droplets have charges that can move. So the idea is if you've got two positively charged droplets, they will each induce a negative charge in the other drop. And so this is actually attractive. It's only valid at small, short-range forces. but it does certainly theoretically have an effect on how droplets how they can collide with each other. And it tends to be, it's a larger effect for small droplets, so typically droplets that are smaller than 10 microns. So this is showing that for the smallest droplet sizes here, as we increase the charge, the collision efficiency gets larger. So these are the two ways that we think that charge might affect cloud microphysics. So one of the large-scale clouds processes that we can model, and we've started to do this now, is rainfall and what the effect of charge has on rainfall. So this plot here is modeling the time that it takes for droplets to grow to a size where they're raindrops. They're big enough to be raindrops, so that's about 500 microns. And if you add charge into this, what you find is that the drops reach raindrop size quicker if they're charged than if they're uncharged. And it's not a huge amount faster, but it is faster.